Namaste, my friend, and welcome back to JEE Physics with Typical Monk. This is class 5, and today we finally answer a question every student asks quietly. What does force actually buy you? A push tells you how hard you shove something. What tells you what that shove actually purchases? A gain in speed, a spring squeezed tight, a height climbed against gravity. Sarah once wrote the right force equation on a variable force problem and still lost the mark, because she multiplied force by distance the way you would for a constant push, when the force itself kept changing along the way. Today, we fix that with one clean idea: the integral of f dx. And everything else in this chapter, kinetic energy, potential energy, power, falls out of it naturally. Take a slow breath. Let us begin. So what will you carry home from today's class? First, work by a variable force, written as an integral, the sum of tiny slices of force times displacement. Second, the work energy theorem, net work done on a particle always equals the change in its kinetic energy, and this never fails, no matter which forces are acting. Third, conservative versus non-conservative forces, and how potential energy is born from force equals minus the derivative of u with respect to x. Fourth, energy diagrams, reading stability straight off a graph of potential energy against position. And fifth, power as force started with velocity, and the potential energy tucked inside a compressed or stretched spring. Ready? One idea at a time. Let us meet the 4 ideas that carry this entire chapter. First, work by a variable force. Slice the motion into tiny steps of width dx, multiply each by the force at that instant, and add every slice. That sum, taken to the limit, is the integral of f dx. Second, the work energy theorem. Add up the work done by every single force acting on a particle, and that total always equals the change in its kinetic energy, a shortcut that skips accelerations entirely. Third, potential energy. Only a conservative force earns 1, and that force is always the negative slope of u with respect to x. It points downhill on the energy landscape. And fourth, instantaneous power, force dotted with velocity, the rate at which work is being done at this exact instant, nothing more, nothing less. Look carefully at this graph, because it is the picture behind every variable force problem you will ever meet. Force sits on the vertical axis, position on the horizontal one, and the curve traces how the force changes as the particle moves. Zoom into one thin strip of width, dx. Its height is the force at that point, so its area is a tiny piece of work, w pi dr. Now add every strip together from the starting position to the final one, and in the limit of infinitely thin strips, that sum becomes the integral of f dx. The total work is simply the area trapped under the curve. David used to panic whenever a force was written as a function of x instead of a plain number. Once he saw that a constant force is just this same picture with a flat curve, so the area collapses into a plane rectangle, force times displacement, he realized he already knew the special case. He just needed the general one. And here is the twist G loves. Wherever the curve dips below the axis, that patch of area counts as negative work, and it is subtracted, never ignored. Now, which forces even get to have a potential energy? And what does that curve tell us about balance? First, a conservative force. Move a particle between 2 points by any path you like, and the work done by a conservative force is exactly the same every time. It depends only on where you started and where you ended. Second, the defining relation. Force equals minus 2 by dx. The force always pushes toward lower potential energy, downhill on the u of x curve, and the minus sign is not optional. It is the whole idea. Third, equilibrium. Wherever the slope du by dx is 0, the net force vanishes, but a valley, a minimum of u, gives a stable equilibrium, while a hill, a maximum of u, gives an unstable one. And fourth, a flat stretch of u gives neutral equilibrium, where the particle feels no restoring push either way. Friction, meanwhile, is non-conservative. It has no potential energy at all, because its work depends on the length of the path traveled, not just the displacement. Time to solve a full G numerical together, slowly, the monk's way, and this time, the force itself keeps changing. A force F of x equals A times x minus b times x squared acts on a particle as it moves from x equals 0 to x equals L. Find the work done. Step 1. Write down what is given. The force is a times x minus b times x squared, and the particle travels from x equals 0 to x equals L. Step 2. The formula. Because the force is not constant, work is not simply force times distance. It must be the integral of f dx, taken from 0 to L. Step 3. Integrate. The integral of a times x is a times x squared over 2, and the integral of b times x squared is b times x cubed over 3. So w equals a x squared over 2 minus bx cubed over 3. Step 4. Substitute the limits. At the lower limit, x equals 0. Every term vanishes, so only the upper limit at x equals L survives. Step 5. The answer. W equals L squared over 2 minus BL cubed over 3. Notice the method. Given, formula, integrate, substitute, answer. The same 5 moves solve every variable force numerical G can throw at you. Now watch energy trade forms as a block slides down a curved, frictionless track and squeezes a spring at the bottom. At the top point A, the block sits at rest. All of its mechanical energy is potential, and none of it is kinetic yet. Partway down, at point B, the block has lost some height and gained some speed. Potential energy is converting smoothly into kinetic energy, and the two bars you see always add up to the same total height. At the bottom, point C, the height is 0, so every bit of energy has become kinetic. The total never changed. It just moved from one bucket to the other. And then, the spring takes over. As it compresses by a distance x, that kinetic energy is stored once again, this time as spring potential energy, equal to 1/2 kx squared. Lisa used to think energy simply disappeared into a spring. Once she saw it as the very same potential energy bucket, just refilled by a different force, the whole picture clicked for her. Now sit up straight. These 5 lines are what JEE actually asks, year after year. 1. The work energy theorem, net work equals the change in kinetic energy, holds for every force acting on the particle, conservative or not. It never fails. 2. A conservative force always has a potential energy, and its work done around any closed loop is exactly 0. A favorite trick question. 3. Spring potential energy is 1/2 kg squared, and it is always positive, with x measured from the spring's natural unstretched length. 4. Wherever du by dx is 0, look at the second derivative of u. Positive means the point is stable, negative means it is unstable. 5. Instantaneous power is force started with velocity, and it turns negative the moment a force points opposite to the motion, even if the force itself never changes. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion, the work done by gravity between 2 fixed points is the same no matter which path is taken. Reason, gravity is a conservative force, so its work depends only on the initial and final positions. Think like Sarah. Check each statement, then the connection. Is the assertion true? Yes. Is the reason true? Yes. Does the reason explain the assertion? Completely. Path independence is exactly what makes a force conservative. Both true. Reason explains. Option A. Second one. Assertion, the potential energy stored in a spring stretched by x is the same as if it had been compressed by that same x. Reason, the work done against a conservative force equals the rise in potential energy. Both statements are true. But pause, does the reason explain the assertion? No. The symmetry of the stretch and the compression comes from x appearing squared in the spring energy formula, not from this general statement about conservative work. Both true, but the reason does not explain the assertion. Option B. This is the trap that catches John every time. Third one. Assertion. At every equilibrium point of a particle, The potential energy U of x is a minimum. Reason: a stable equilibrium corresponds to a minimum of the potential energy function. Check the reason first. That is exactly the definition of a stable equilibrium. True. Now, the assertion: equilibrium can also sit at a maximum of U, which is unstable, so not every equilibrium point is a minimum. The assertion is false. The reason is true. Option D. A quick match now. Say each result aloud before I reveal it. The work energy theorem: net work equals the change in kinetic energy. A conservative force equals minus 2 by dx. Spring potential energy, 1/2 kx squared. And instantaneous power, force dotted with velocity. If all four came to you before the reveal, this chapter is becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. The work done by a conservative force around any closed path is 0. Hold your verdict. Statement 2. The work energy theorem applies only when every force acting is conservative. Think carefully before you answer. Statement 3. A point where du by dx is 0 and the second derivative of u is negative is an unstable equilibrium. Picture the top of a hill on the u of x curve. So, how many are correct? Two statements, the first and the third. A conservative force truly does 0 net work around a closed loop, and a negative second derivative truly does mark an unstable equilibrium, the top of a potential hill. But the second one, false. The work energy theorem does not care whether the forces are conservative, it always holds. Two correct, and the middle one is the trap. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. Friction's work can be worked out from displacement alone, the same way it is found for a conservative force. It feels natural. Friction is just another force. Why treat it differently? But here is the truth. Friction is non-conservative. Its work depends on the actual length of the path traveled, not merely on how far the particle ended up from where it started. Two paths with the same displacement can lose very different amounts of energy to friction. Myth 2. If part of an fx graph dips below the axis, that stretch of the motion simply contributes 0 work, since nothing seems to be pushed there. The truth: area below the axis is negative work, and it is subtracted in full. It does not vanish, it actively fights against the rest of the motion. One myth, one full G question. Do not let it be the one that costs you. Time to test yourself, rapid fire, and every answer today is a number. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just what you built today. Question 1. A force F equals 10x newtons acts on a particle from x equals 0 to x equals 2 meters. What is the work done? Integrate 10x from 0 to 2, 20 joules. Question 2. A 2 kilogram block moving at 4 meters per second is acted on by a net force doing 20 joules of work. What is its final speed? Initial kinetic energy is 16 joules. Add 20 to get 36. Solve for speed 6 meters per second. Question 3. A spring with K equal to 200 newtons per meter is compressed by 0.1 meters. What potential energy does it store? 1/2 times 200 times 0.1 squared, 1 joule. Question 4. A 50 Newton force acts on an object moving at 4 meters per second along the same direction as the force. What is the power delivered? 50 times 4, 200 watts. And question 5. The thinker. Potential energy U of x equals x squared minus 4x in joules with x in meters. Where is the equilibrium and what kind is it? Take the derivative, 2x minus 4, set it to 0, x equals 2 meters. The second derivative is positive 2, so it is a stable equilibrium. If you caught that one, you have truly understood today's class. Let us gather the whole class in one slow breath. What by a variable force is the integral of f dx, the signed area trapped under the fx graph. The work energy theorem holds no matter what. Net work always equals the change in kinetic energy. Conservative forces store energy as potential energy through force equals -2 by dx, and friction simply cannot. Equilibrium sits wherever 2 by dx is 0, a minimum is stable, a maximum is unstable, and a flat stretch is neutral. Power is force dotted with velocity, and a spring stores 1/2 kx squared of potential energy the instant it is stretched or compressed. And next class, we meet the center of mass, momentum, and collisions. Know how a whole system of particles can be tracked by one single point, how momentum survives even the messiest collision, and how elastic and inelastic collisions differ. Do not miss it. And so, my friend, you now know exactly what force is. It may have started as a single integral, the area under a curve, but understand this: every kinetic energy, every stored spring, every stable value on a potential energy graph, all of it grows out of that one idea. Sarah, David, Lisa, and John all once stared at a variable force and froze, exactly where you might be right now, and each of them got past it with this one chapter. Be patient with yourself. Tonight, revise the chain once, slowly. Work is the integral of f dx. Net work becomes change in kinetic energy, and a conservative force always hides a potential energy inside it. One idea at a time. You will crack G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you at the center of mass.